Welcome to today's problem walkthrough. In this session, we'll tackle minimum domino rotations for equal row, a problem that challenges us to determine the minimum number of rotations required to make all the numbers in either the top row or the bottom row of dominoes the same. Let's dive into the details and explore some efficient solutions. This problem involves two rows of dominoes, represented by the integer arrays tops and bottoms. Each domino has a number on its top half and another on its bottom half, as described by tops, I, and bottoms, I. For instance, if a domino shows 2, 5, rotating it flips the numbers to 5, 2. The goal here is to figure out the minimum number of rotations needed to make all the numbers in either the tops array or the bottoms array identical. If it's not possible to achieve this uniformity, we need to return -1. This means we're working with constraints that require us to rotate dominoes strategically to align the values in one row while minimizing the number of changes. Let's explore the first example to understand this problem better. We're given tops equals 2, 1, 2, 4, 2, 2, and bottoms equals 5, 2, 6, 2, 3, 2. The output is 2, meaning 2 rotations are sufficient to make all the values in the tops array equal to 2. For example, we can rotate domino 0 to change 2, 5 into 5, 2, and domino 3 to change 4, 2 into 2, 4. After these rotations, the tops array becomes 2, 2, 2, 2, 2, 2, and while the bottoms array remains unchanged, our condition for uniformity in the tops row is satisfied. Alternatively, we could focus on making all the values in the bottoms array equal to 2 using the same 2 rotations. Now, let's consider another example where tops equals 3, 5, 1, 2, 3, and bottoms equals 3, 6, 3, 3, 4. In this case, the output is -1, indicating that it's impossible to make all the values in either row the same. No matter how we rotate the dominoes, there's no single number that can dominate either the tops row or the bottoms row. In the third example, we're given tops equals 1, 2, 1, 1, 1, 2, 2, 2, and bottoms equals 2, 1, 2, 2, 2, 2, 2, 2. The output here is 1, meaning only one rotation is required. Specifically, we can rotate domino 0 to change 1, 2 into 2, 1. This ensures that all the values in the tops row become uniform, with tops equals 2, 2, 1, 1, 1, 2, 2, 2, and bottoms remaining the same. This example highlights that the minimum number of rotations is not fixed but depends on the initial arrangement of the dominoes. Finally, there are some key constraints and edge cases to keep in mind. First, the lengths of tops and bottoms will always be equal, ranging from 2 to 20,000. Each number in the arrays is between 1 and 6, corresponding to the values on a standard domino. Edge cases include scenarios like the minimum input size, where tops and bottoms have only 2 elements, and cases where no valid rotations exist to make a row uniform. We also need to handle situations where all elements are already equal, requiring 0 rotations, and ensure our solution remains efficient even for the largest inputs near the upper constraint of 20,000 dominoes. To solve the problem of determining the minimum number of rotations required to make all numbers in either the top or bottom row of dominoes the same, we considered several approaches. The most straightforward one is the brute force method. Here, we examine all possible values that could fill an entire row. These values range from 1 to 6, since domino values are constrained to this range. For each potential value, we calculate the rotations needed to make all elements in either the top or bottom row equal to that value. The goal is to find the minimum among these computed rotations. The time complexity for this method is O(n), where n is the number of dominoes, as we iterate through the arrays for each potential value. Additionally, this approach requires constant space, making it memory efficient. However, while simple, there is an opportunity to optimize further by narrowing down the potential candidates we check. A more efficient solution focuses on reducing the number of candidates to check. Instead of iterating over all values from 1 to 6, we recognize that only the numbers at the first domino, either tops, 0, or bottoms, 0, can potentially fill the entire row. If a number is not present in the first domino, it cannot be the target value for the whole array. This insight allows us to limit our candidates to at most 2 values. For each of these candidates, we calculate the minimum rotations needed to make all values in either the top or bottom row equal to that candidate. While doing this, we make key observations. If the candidate number does not appear in at least one of tops I or bottoms I for any index, that number is disqualified. Additionally, no rotation is needed for a domino if it already matches the candidate. By iterating through the arrays a constant number of times, this approach achieves linear time complexity with constant space, offering both efficiency and clarity. An alternative approach involves leveraging frequency counts of numbers in the tops and bottoms arrays. This method calculates the maximum possible occurrences of each number across both rows, while also accounting for overlaps where the same number appears in both tops I and bottoms I. While this technique is valid, it is less intuitive and requires additional bookkeeping to track these counts and overlaps. As a result, it is more complex to implement compared to the candidate-based method. Despite its linear time complexity and constant space usage, the added complexity of managing frequency counts makes it a less practical choice for this problem. Ultimately, while this approach is an option, it was not selected due to its reduced simplicity and clarity. When comparing the approaches, the optimized method stands out as the most practical. The brute force approach checks all numbers from 1 to 6, while the optimized method narrows this down to just two candidates, tops 0 and bottoms 0. Although both approaches have the same worst-case time complexity of O(n), the optimized method is more efficient in practice due to the reduced number of checks. On the other hand, the frequency count approach introduces valid insights but requires managing multiple counters, making it less intuitive and harder to implement. By focusing on the potential candidates from the first domino, the optimized approach achieves a balance between efficiency and simplicity. This makes it the best fit for solving the problem effectively while keeping the implementation straightforward. In this problem, we need to determine the minimum number of rotations required to make all the numbers in either the top row or the bottom row of a domino sequence the same. Each domino has two numbers, one on the top and one on the bottom. A rotation at any position means swapping the numbers at that specific index between the top and bottom rows. If it is not possible to make all the numbers in either row identical, we return -1. To solve this, the first step is to understand the feasibility of the problem. For a solution to exist, there must be at least one number, called the target, that can dominate either the top or bottom row after some rotations. The candidates for this target are restricted to the numbers in the first domino, top 0 and bottom 0, since any valid solution must involve making one of these numbers dominate the sequence. From here, our task becomes one of candidate checking. First, we check if it's possible to make the sequence homogeneous using top 0 as the target. If that fails, we then check with bottom 0 as the target. Now, to determine the number of rotations required for each candidate, we iterate through all the dominoes. For each target, we count the rotations needed in the top row to make all the values equal to the target, and separately count the rotations needed for the bottom row. However, if at any index both top I and bottom I fail to match the target, it becomes impossible to make the sequence homogeneous with that target, and we can discard it immediately. This optimization allows us to stop early and avoid unnecessary computations. Once we've processed all the dominoes for both candidates, top 0 and bottom 0, we simply compare the rotation counts and return the minimum. Additionally, there are a couple of edge cases to handle. If all dominoes already have the same number in one row, the result is 0 as no rotations are needed. On the other hand, if no valid solution exists, we return -1. The algorithm is efficient because it leverages several key insights. First, the candidate reduction principle ensures we only need to check two numbers, top 0 and bottom 0, rather than all possible numbers in the sequence. This drastically simplifies the problem. Second, early pruning helps us exit the computation as soon as we determine that a target is invalid for any domino. This avoids unnecessary work and speeds up the process. Finally, the entire solution only requires two passes over the domino sequence, one for each candidate, which makes it highly efficient. In terms of data structures, we use the input arrays directly for comparisons and indexing, while two counters, rotations_top and rotations_bottom, keep track of the rotations required for each candidate. Regarding complexity, the time complexity is O(n), where n is the number of dominoes, since we perform a single pass for each candidate. The space complexity is O(1), because we use a constant amount of extra space. Let's walk through a concrete example. Suppose we are given the input arrays top equals 2, 1, 2, 4, 2, 2, and bottom equals 5, 2, 6, 2, 3, 2. The first step is to identify the candidates for the target, which are top 0 equals 2 and bottom 0 equals 5. Now, we check the first candidate, target equals 2. For each domino, we determine whether a rotation is needed to make the target dominate. For the first domino, top 1 equals 1 and bottom 1 equals 2, so we rotate to make bottom 1 equals 2. For the second domino, no rotation is needed because top 2 already equals 2. For the third domino, top 3 equals 4 and bottom 3 equals 2, so we rotate to make bottom 3 equals 2. For the fourth domino, no rotation is needed because top 4 equals 2. Finally, for the fifth domino, both top 5 and bottom 5 are already 2, so no rotation is needed. In total, we find that 2 rotations are required to make the bottom row homogeneous with the target 2. Next, we check the second candidate, target equals 5. Starting with the first domino, we see that top 1 equals 1 and bottom 1 equals 2. Here, neither top 1 nor bottom 1 matches the target 5, meaning it is impossible to make the sequence homogeneous with this target. At this point, we can stop checking further dominoes for this candidate. Since target equals 5 is invalid, we don't consider it any further. Comparing the results, the minimum number of rotations required is 2, which we found while checking target equals 2. Therefore, the final result is 2, and this is what we return as the output. Here, we define a Python class called solution and implement the function minDominoRotations, which takes 2 lists, tops and bottoms, representing the top and bottom halves of dominoes. The goal is to determine the minimum number of rotations needed to make all the numbers in one row equal. Inside this function, we define a helper function called count_rotations, which calculates the number of rotations required to make all elements in the domino rows equal to a specific target value. This helper function iterates through the dominoes to check each position. If neither the top nor the bottom of a domino contains the target value, the function returns infinity, as it's impossible to make all values equal. Otherwise, it counts how many rotations are needed to align either the top or bottom values with the target. Finally, it selects the smaller rotation count between the two options. After defining the helper function, we use it to calculate the rotations needed to align all values to the first element in the top's array and the first element in the bottom's array, treating these as potential candidates for the target value. The next step is to determine the result. We compare the minimum rotation counts obtained for the 2 target candidates, tops 0 and bottoms 0, using the min function. This gives the smallest number of rotations required to make all values equal for either candidate. If the result remains infinity, it indicates that it is impossible to align all values in either row, so we return -1. Otherwise, we return the calculated minimum rotation count as the final result. This completes the implementation, providing an efficient method to solve the problem by focusing on only 2 potential target values and minimizing unnecessary computations. Here, we begin implementing the solution in Java. The minDominoRotations method takes 2 integer arrays, tops and bottoms, representing the top and bottom halves of a row of dominoes. To solve this problem, we define a helper method, countRotations, which calculates the number of rotations required to make all values in a row equal to a given target. Inside this helper method, we initialize counters for rotations needed in the top and bottom rows. Using a for loop, we iterate through the dominoes. If neither the top nor bottom value of a domino matches the target, we return integer.max_value, indicating that it's impossible to achieve the desired configuration. Otherwise, we increment the respective counter if the current top or bottom value doesn't match the target. Finally, the method returns the minimum of the rotations needed for the top or bottom row. Now, we use the countRotations helper method to determine the minimum rotations required for 2 potential candidates, tops 0 and bottoms 0. These values represent the top and bottom of the first domino, which are the only feasible targets for aligning all dominoes. We calculate the rotations needed for each candidate and store the results in rotations top and rotations bottom. The overall result is the smaller of these 2 values. If both candidates are impossible, meaning the result equals integer.max_value, we return -1 to indicate that it's not possible to make all values in the row equal. Otherwise, the result is the minimum number of rotations required to align the dominoes. Here, we begin with an example where it's possible to make all dominoes show the same number by rotating. The input arrays are tops equals 2, 1, 2, 4, 2, 2, and bottoms equals 5, 2, 6, 2, 3, 2. The first step is to initialize a helper function, count_rotations, which calculates the minimum number of rotations required to make all dominoes show a specific target number. The two initial target candidates are tops, 0, equals 2 and bottoms, 0, equals 5. We start by evaluating tops, 0, as the target, which is 2. Inside count_rotations, target equals 2, we iterate through each domino. For I equals 0, the top already matches the target, so no rotation is needed. For I equals 1, the top doesn't match, but the bottom does, so we rotate the top, increasing top_rotations to 1. For I equals 2, the top matches again, so no rotation is required. At I equals 3, the top doesn't match, but the bottom does, so another top rotation is added, making it 2 rotations in total. Finally, for I equals 4 and I equals 5, the top already matches, so no further rotations are needed. The result for target 2 is the minimum of top_rotations and bottom_rotations, which is 2. Next, we evaluate the second target candidate, bottoms, 0, equals 5. With target equals 5, the function checks each domino again. At I equals 0, the bottom already matches the target, so no rotation is required. However, at I equals 1, neither the top nor the bottom matches the target. This makes it impossible to achieve the target number 5, and the function immediately returns float, inf. Since the second target is invalid, we compare the results for the two target candidates. The rotations required for target equals 2 are 2, while target equals 5 is invalid with a result of float, inf. The overall result is the minimum of these two values, which is 2. Thus, the output for this example is 2. Now, let's consider a second example where it's impossible to make all dominoes show the same number, regardless of rotations. The input arrays are tops equals 3, 5, 1, 2, 3, and bottoms equals 3, 6, 3, 3, 4. We first evaluate tops, 0, as the target, which is 3. Using count_rotations, target equals 3, we start checking each domino. For I equals 0, the top already matches the target, so no rotation is needed. However, at I equals 1, neither the top nor the bottom matches the target, which makes it impossible to achieve the target number 3. The function immediately returns float, inf, and we conclude that target equals 3 is invalid. Next, we evaluate the second target candidate, which is bottoms, 0, equals 3. Following the same process as before, we find that the function again returns float, inf, because there's at least one domino that cannot match the target. At this point, both target candidates have failed, with results of float, inf, for both rotations_top and rotations_bottom. Since neither target is achievable, the final result is -1, indicating that it is impossible to make all dominoes equal. The output for this example is -1. Now, let's examine a simpler case where all dominoes are already equal without requiring any rotations. The input arrays are tops equals 1, 1, 1, 1, and bottoms equals 1, 1, 1, 1. For this case, we first check tops, 0, as the target, which is 1. Inside count_rotations, target equals 1, we iterate through all dominoes, and since all the top elements are already equal to the target, no rotations are needed. Both top_rotations and bottom_rotations remain 0. The minimum rotations for this target are min, top_rotations, bottom_rotations, equals 0. Next, we evaluate bottoms, 0, as the target, which is also 1. Repeating the same process, we again find that no rotations are required, resulting in 0 rotations. Finally, we compare the results for both targets. Since both rotations_top and rotations_bottom are 0, the overall result is min, 0, 0, equals 0. This means the dominoes are already equal, and no rotations are necessary. The output for this example is 0. The time complexity of this solution is O(n), where n represents the length of the input arrays, tops or bottoms. To break this down, the helper function count_rotations, target, iterates through all elements of the arrays once, performing constant time operations like condition checks and counter increments for each index. This results in a time complexity of O(n) per call. In the main function, this helper is called twice, once for tops, 0, and again for bottoms, 0. Since each call takes O(n), the total time complexity becomes O(n) plus O(n), which simplifies to O(n). However, in big O notation, constants are ignored, so the overall time complexity is O(n). The algorithm maintains a time complexity of O(n) in the best, average, and worst cases. This is because the number of iterations is always proportional to the length of the input arrays, regardless of their actual values. Mathematically, the algorithm performs at most 2 linear scans of the arrays, with each scan involving simple operations like comparisons and increments. This linear growth rate confirms an O(n) complexity. As for space complexity, the solution uses O(1) constant space. This is because it does not require any additional data structures that grow with the input size. All variables, such as top_rotations, bottom_rotations, and target, use a fixed amount of memory, irrespective of the input size. The space complexity remains constant at O(1) across all cases best, average, and worst, since the algorithm's memory usage does not depend on the size or content of the input. To break it down, the input array's tops and bottoms are provided as input and do not contribute to additional space. Temporary variables such as counters or the target value also require a fixed amount of memory, which does not scale with the input size. This means the algorithm processes the input arrays directly without using any auxiliary arrays, hash maps, or other data structures, ensuring constant space usage. A brute force approach to this problem would involve iterating through all possible domino face values, from 1 to 6, and checking for each value whether it can make the tops or bottoms array uniform. For each of the 6 values, the algorithm would perform a full scan of the arrays to count rotations. This results in a time complexity of O(6*n), which simplifies to O(n), as the constant factor 6 is ignored in big O notation. The space complexity for the brute force approach remains O(1), as no additional data structures are used. In contrast, the optimized solution reduces unnecessary checks by focusing only on the values of tops, 0, and bottoms, 0, as potential targets. This avoids iterating through all 6 values and directly narrows down the possibilities. As a result, the optimized approach achieves the same O(n) time complexity but with cleaner and faster execution for larger inputs, making it more efficient overall. When solving this problem, there are a few common mistakes that can trip up even experienced coders. First, many people fail to consider all potential candidates for unification. For example, they might only check the number on the first domino and assume that's enough. However, the correct approach requires evaluating every number that appears in the dominoes, as any of them could potentially lead to the minimum number of rotations. Ignoring this step narrows your search too early and can result in missed solutions. Next, there's the issue of invalid configurations. Sometimes it's simply impossible to unify the rows, such as when no number appears consistently across the dominoes. If your code doesn't account for such edge cases and return -1 as specified, it's incomplete. Another frequent issue is incorrectly updating rotation counts. Remember, rotating a domino impacts only one row, the top or the bottom, so it's vital to track these rotations separately. Treating them as interchangeable can lead to inaccurate results, so attention to detail here is key. Another pitfall to watch out for is relying on inefficient brute force approaches. Some solutions use nested loops to check all possible rotations for every domino index, which results in a time complexity of O(n²). While this might work for small inputs, it's far too slow for larger cases. The good news is that you can solve this problem in O(n) time by focusing on candidate numbers and scanning the array just once. Additionally, a common misinterpretation of the problem is assuming you need to rotate all dominoes. In reality, the goal is to unify a single row with the minimum number of rotations. Selective rotations are enough to achieve this, and trying to rotate every domino introduces unnecessary complexity. Being clear about the objective helps you avoid these extra computations and keeps your solution efficient. Now let's focus on some practical insights for interviews. The key takeaway here is that the problem can be simplified significantly by reducing your checks to just the numbers in the first domino. If unification is possible, it will involve one of these values, which saves a lot of unnecessary work. To optimize further, you can use a single pass through the array to calculate the rotations needed for each candidate value. This approach minimizes redundant checks and ensures an O(n) time complexity. It's also important to consider edge cases, like configurations where no common value exists, rows that are already unified, or situations where no rotations are needed. Highlighting how your solution handles these scenarios demonstrates thoroughness and a strong command of the problem. Finally, when explaining your approach, make sure to clarify why you focus on the first domino's values as candidates. This shows your understanding of the problem's constraints and your ability to streamline the solution. If you're preparing for related problems, you might find it helpful to study others like height checker or non-decreasing array, which also involve minimal operations to meet certain conditions. When it comes to alternative approaches, the brute force method is the most intuitive place to start. This involves trying all possible rotations for each domino and calculating the total rotations required for every candidate number. While this is straightforward to implement, it's computationally expensive with a time complexity of O(n squared, making it impractical for larger inputs. A more efficient solution is the optimized single-pass approach. Here, you focus only on the values in the first domino as potential candidates and count the necessary rotations in a single pass. This reduces the time complexity to O(n), but requires careful attention to detail, especially when tracking rotation counts and handling edge cases. Another option is the hash map approach. By storing the frequency of each number in both rows, you can quickly determine the minimum rotations needed for unification. While this approach also runs in O(n) time, it uses extra space for the hash map, which might be a trade-off to consider. Each of these methods has its strengths, so understanding their trade-offs will help you decide which approach is best for a given context. Great job! We've successfully explored the problem minimum domino rotations for equal row. To recap, we used an efficient algorithm to determine the minimum rotations, leveraging candidate values and minimizing operations. Remember to practice similar problems for mastery. Thanks for watching, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!